The top of a dark plate exposed to the sun is being subjected to 800 watts per meter squared of heat. All the heat is being dissipated at a constant heat flux through the bottom of the plate only, due to airflow of 25 Celsius flowing at 3 meters per second. The plate is 25 centimeters square. So once again, that weird way of saying that something is 25 by 25. What is the average temperature of the plate, and what is the heat transfer coefficient at 5, 10, and 25 centimeters from the front of the plate? So the reason why I have this guy here is because this is a very situation is very similar to a solar panel, a PV panel, right? So you can imagine it's receiving 800 watts per meter squared from the sun at any given point. Obviously, this changes throughout the day, but just for the sake of our analysis, that's good enough. And through the back of the plate, so the back of the plate here, we have air, and it's going through the back of the plate and coming on the other side, and it's carrying away some of that energy, right? So that the thing would not increase in temperature as time elapses. So on my beautiful drawing, we have the same thing now here, but we have a problem, and the problem is that we can't really get the temperatures, the properties like before, right? Because we can't really find T film at this time because we don't have T wall. So because we don't have T film, we can't really grab the properties at the average between the T wall and the air. So in this case, what we're going to do is we're going to assume the properties at 25 Celsius, which is the temperature of infinity, knowing that that is incorrect. Okay, so that's why I wrote down here. We're going to assume the properties of air are at T infinity, knowing it is wrong to do so. Okay, so we're going to grab the properties at 298 Kelvin, which is the same thing as 25 Celsius. Okay, so I grabbed properties from table A5 at 298 Kelvin. Now, I know that this plate has to be at a higher temperature than the air for the air to be able to remove temperature energy from the plate, right? But I don't know at which temperature that is. So doing this assumption is fine when I have an idea of the situation so that I can iterate a couple of times. So what do I mean by that? Well, I know this solar panel is not going to be at 400, 1500 Celsius, something like that. I know it's going to be in a margin of about 100 of my air, right? So because of that, this method is good enough. But if I had no idea, if I'm talking about a furnace or a situation that I have no idea what I'm dealing with, I'm just touching the dark trying to find some clues, this method could render some very off results because you can fall into one of those traps, those function traps in which you are always interacting to find the average value, but you're on a valley, right? So you have to go to the extremes to be able to find your value. So don't worry too much about what I'm saying if you don't get what I'm trying to explain mathematically. What I'm trying to say in simple ways is what we're doing here is we're assuming something that we know to be wrong, and we're going to correct as we go. Okay, so I just grabbed these properties for air at 25 Celsius, and I know this is a non-isothermal with constant heat flux coming through, so I'm plugging in the same equation we just used before. Okay, I'm plugging in once again the same thing we just did before, and that one is telling us that the temperature of the wall minus T infinity, the average between these two, equals this constant heat flux going into or out of the thing over the whole length of the plate, the conductivity of the fluid, Reynolds and Prandtl. We have everything here except for Reynolds, so we can calculate Reynolds using these properties. And this is the first thing we're doing that we know is incorrect, right? We know this Reynolds is not precisely the Reynolds of this problem, but we need to know where to start. So let's do velocity, length, density. So this will be 1.1774. The velocity of this fella is, forget, 3. It's 25 by 25, so this is a 0.25 in length. And the viscosity of this guy is 1.846 times 10 to the minus 5. So Reynolds ends up being 4.8 times 10 to the 4th. That's very much below critical, so we know this is a laminar flow. Laminar flow. Okay, so we have a bit more information about this problem now. I know that Reynolds is not precisely 4.8 times 10 to the fourth, but even by tweaking the properties there, and we're going to do that in a moment, I wouldn't expect it to increase tenfold, right? So that it will become turbulent. So that already gives me a better idea. So with that, then I can be safe to use this laminar equation here. All right, so I'm going to plug in the values for that guy there. T wall, which I'm looking for, I don't know, minus T infinity, which is 27 or 298 Kelvin, has to be equal to the flux of energy coming in times L divided by my conductivity, 2624, and then 0.6795 Reynolds being 4.8, halved, and this is 0.78 to the third. Okay, so this means that this guy is approximately 57.44. That is a difference in Kelvin or Celsius, right? Difference in Kelvin Celsius. So therefore, T wall equals 298 plus 355.44. Okay, so now what we do, now we just have a value for T wall, a value that we know is not correct, it's not precise, but it's a starting point. It gives us a little indication of what we have. Another option could have been, you could have guessed this guy was at, I don't know, at 100. And you have to work your way from there downwards. Okay, this in Celsius, this is about what? I don't even know, 50 something Celsius? 355, 82 Celsius. Okay, so if you guessed 100, you have to go back down a couple of steps. Now, what do? Now we do everything again, right? That's why it's called iteration. We're going to do the whole thing again. Now we're going to take new film temperature, T film, because now we know we have air at 298, and we also have a wall that should be somewhere around 355. And we divide that by 2. That's going to give me 326.7. Okay, so now I'm going to grab new properties. And I'm going to do the whole thing again. And I'm going to grab a new T-wall. And we're going to evaluate that T-wall and see if we need to do this again or how many times we would need to do that. So luckily for you, I already did that with the previous class. So these are the properties at 326.7. And then I can calculate Reynolds. And my Reynolds decreased. So if you guys recall, it was 4.8. And now it's 4.1. Okay. Before we move on, it's probably a good idea to see how these values change. So my density was 1.846. Sorry, no, my density was 1.1774. My conductivity was 0.02624. Prandtl was 0.708. Density was 1.846. 20 10 to the minus 5, right? So significant change in the properties. Okay, we had a change in the Reynolds, but still laminar. And then we go once again, we do the whole thing once again, plug everything. What's going to change? Well, our K will change, right? Our K has changed, and our Reynolds has changed, and our Prandtl has changed. So we would expect a new T-wall value. And our new T-wall value is 356.4 Kelvin. So if you guys recall, we just found 355, and now we have found 356. Okay, so what do we need to do now? Well, we need to do it one more time. Yes or no? Well, it depends. It's up to you guys to see if you need to do it one more time or not. Okay, this is up to interpretation once again. From 355 to 56, it's a small difference. If you think about it, let's think about it with a little bit numbers going up. Oops, that's not what I want. I want clean. Let's see what will be our new film temperature. 298 plus 356.4 divided by 2. $327.2. Okay, so that will be our new properties will be at that temperature. Remember the previous one we had? 326.2. So the properties won't change. They would only change slightly, I should say. So therefore, my Reynolds won't change much, and my TOL won't change much. But you're welcome to do it one more time. I actually did it one more time when I was solving it, and indeed, it's going to just stay where it is. So we can stop there and be like, okay, I'm going to assume that my temperature on my wall is 356.4. Questions around this? Okay, so now we are happy with the temperature of the wall that we found, and we're happy with the properties that we have. Okay, because we know they're not going to change. They're only going to change slightly from 326.7 to 327.2. So now we can jump into part B, and part B is asking us, okay, what is H at X equals 5 centimeters, 10 centimeters, and 25 centimeters? Okay, so we need to find all those guys. Well, that's straightforward, right? Remember that under these circumstances, we have that equation, the one that we found for the previous question too, which is the Nusselt at any given point will be 0.453 times the Reynolds at any given point, half times Reynolds to the 1/3. Okay, so that means that for any H that we want to find, we can find our proper Nusselt and then multiply by the proper Reynolds. The only thing you need to be aware of is that if you change from 5 to 10, for instance, our Reynolds also changes, right? So you can't use the same Reynolds every single time. I can see how a student would be tempted to, where's my Reynolds? To use this value here, 4.1, but this is for the 25 centimeters, right? So this is for the whole length of the plate. If we are at a different part of the plate, that will have a different Reynolds. So we need to do one Reynolds at a time. So the first Reynolds, let's do this one at 5. It's 5 centimeters. My Reynolds will be Reynolds at 5 centimeters. 5 centimeters. Okay, so our density, obviously, the density is not going to change regardless of how far we are on the plate. That's good enough. So let's grab my properties. The velocity doesn't change either. What was the velocity? 2? 3 meters per second? 3 meters per second. But then this guy changes, right? 0.05 for it to have it in meters. The viscosity does not change either, so 1.96.10 cents to minus 5. So I got this Reynolds to be 8,265, which, mind you guys, is very different from the 4.1 times 10 to the 4th we had before. And now with that, I can find Nusselt. So Nusselt at 5 centimeters is 53 times 8,265 half and 0.7025 1/3. My Nusselt is 36.61. And therefore, my H at 5 centimeters is 36.61 times my conductivity divided by the X, in this case 0.05. 20.5. Okay, so that is our first H. If you guys recall, or if you guys look at the graph that I gave you, you see how my H is varying with X, and you see how it varies, how it decreases as our X increases until we reach critical, right? So we have a behavior that is something like this, downwards, and then we reach critical, and then this guy shoots right straight up, and then we see the decline again. Okay, so this will be, right here will be our X critical. And if you think about how convection works, that makes a lot of sense. So let's jump into our next one. At 10 centimeters. So because the whole thing is laminar, I would expect my H to decrease now, right? To be smaller than the 20.5. Reynolds, first thing I need to calculate is Reynolds. Reynolds, everything will be the same, so I can actually do this, be cheeky. Because everything is the same except for this guy here, which becomes 10. Right, so this Reynolds is 1653. This one too. Oh, I reached the bottom of the page. Sorry. Let me just grab $2,000. Should do. So Nussel. Oh, sorry guys. Everything remains the same except for this guy here, which is now 16,536. So my Nussel then becomes 51.77. And in spite of my Nussel increasing, my X decreases, so my H will also decrease, as you'll see. So I have 51.77. 0.028. So this guy is 14.5. And the last one, 25, which is right on the edge of the plate. What changes? This changes to 25 over here. So this whole number will change, 41,326. This number therefore changes. 25 centimeters, 25 centimeters. So this is 41,326. So my Nussel is now 81.92. And then $9.18. So indeed, the behavior we just talked about is what ends up happening, right? Our convective coefficient is decreasing. If you recall, it started as 20, I think. Yeah, 20.5, 14, then 9.18, precisely as predicted, right? So it's decreasing on this region here. If our plate was longer, okay, if the length of it was greater, then we would find at some point that the flow would become turbulent, and then this value would shoot up again, and then it will start to decrease again slowly. Questions on this problem?